In this section, we start doing things using the items from the last section. This section actually starts with the ruler postulate in the book, but that is too dumb for words. Basically, you can make a ruler any size you want in any units you want. So let's move on to things that are actually useful. Hopefully you have seen a coordinate before. In this section, it is referring to coordinates on a number line. I'm guessing you have seen a number line or two before, and that you also know that each tick mark on the number line corresponds to a real number that is the coordinate of the point. This is review, right? You probably also know about distance, how far something is from another. And I am hoping that you have calculated distance on a number line before. Here are 2 points on our number line, A and B. If you want to calculate the distance between the two of them, you certainly can brute force it and just count how many there are between them. But you should have been taught before that distance is calculated with absolute value. No matter which coordinate you start with, the absolute value takes care of you to make sure your final answer is right. So here the distance between A and B is 5, which, yes, is easily done here by brute force also. But sometimes you'll have variables for the coordinates instead of numbers, and you'll be forced to do it the absolute value way. So you definitely need to know absolute value is what can mathematically calculate distance. Now this number line we have been working with on A and B should remind you of line segment AB, which has a length of 5. Let's talk about the issues around lengths of line segments. So here I have line segment AB. It has a length of 5. Here's the thing to keep straight here. Line segment AB is a shape. It's an actual physical thing. Similarly, the other shapes we did in the last section are also shapes. They are also physical things. However, length is a concept or idea. It's the distance between two things. Distance is not a shape. I'm going to be coming back to that a few times in this lesson. And that first time is now. We know that the length of line segment AB is 5, but we don't want to have to write it out all the time. So how about a symbol instead? Last lesson we went over these 3 symbols. So what do you suppose the symbol for length is? Notice that all of the symbols for all 3 shapes are actually the same shape as what they are. However, length isn't a shape. It doesn't have a shape, so its symbol is actually not a symbol at all. It's blank. You don't put anything above the AB. Since length isn't a shape, it doesn't have anything above it. We can now replace this top line with something much shorter. Simply AB equals 5. This brings up a tiny little distinction again. You can only use an equal sign with length. AB equals 5 is okay. A distance can equal a quantity. Distance is a quantity. It is how far apart things are. So you can set them equal. But line segment AB equaling fine is absolutely not okay. A line segment is a shape. Shapes are not distances. Those are different things. You can't set line segments equal to a quantity. It's a tiny distinction that students often have a hard time remembering or wrapping their heads around. I said earlier the ruler postulate is not very useful, but the segment addition postulate is surprisingly useful. You won't really see it in action until we do proofs though. But like most postulates, it's pretty common sense. Here is the official definition. Just reading it may be hard to parse, but it's actually a pretty easy concept. I hope that your teacher isn't one of those that has you spit out the official definitions of postulates. I am one that wants to make sure you understand the concept. The most important thing, and this will come up again when we do proofs, is that you can identify when the segment addition postulate is happening, and you can put a name to it. For now, let's see what this math speak actually means. We're going to take this part of the definition and draw that situation. Here's what that would look like to have A, B, and C collinear, with B in between the other two. With this picture in place, it becomes much easier to see why the conclusion of the postulate is so obvious and basic. You take the left part, and add it to the right part, and it adds up to the whole thing. Well, duh. Next up, we have one of the biggest concepts in all of geometry, the idea of being congruent. It comes up a ton. Congruent means something is the same size and same shape. Both things need to be true in order for something to be congruent. Here are 2 lines. They are going in different directions, and they aren't drawn the same size. But are they congruent? Yes, they are congruent. They are both the same shape, since they are both lines, and they are both the same size. Even though they aren't drawn to the same size, they both go on forever. So because you have checked off both the same size and the same shape requirements, you can definitely say they are both congruent. In fact, any 2 lines are congruent. But it isn't so easy with the line segments. I didn't say it was hard. It isn't just automatic. Here are 2 line segments. First off, they are both line segments, so they are the same shape. Check. One thing we need to see is if they are the same size. For that, we will need some distances. With both of these line segments having a length of 24, that's enough for us to say they are congruent. They are both the same shape and the same size. At this point, we can say that line segment AB is congruent to line segment CD. But who wants to write all that out? Let's bring out a symbol that you will be using a lot. That's certainly a lot better than writing all of that other stuff out. This guy is going to come up all the time. When I ask my students to describe it, I often get an equal sign with a squiggle on top. Now there are going to be times where we want to mark segments congruent without actually saying, or even maybe caring, what their actual lengths are. Here we have our line segments still. To mark them congruent, we use tick marks that look like this. That's all you do to mark the segments congruent. But what happens here? Now I want to mark not just one pair of segments congruent, I want to mark two pairs congruent. The first one is just like the last slide. You mark the first pair with a single tick mark. For the other pair, you can't use a single tick mark again, because that would be saying that all four sides were congruent, and that's not right. Instead, we use the double tick marks to show the second pair are congruent. If there was a third pair to show congruent, you would use triple tick marks, but that's kind of rare. And one time this year, we will have quadruple tick marks, since we will need to show four pairs of line segments congruent at the same time. Our next vocabulary word is a midpoint. Officially, a midpoint of a segment is the point that divides the segment into two congruent segments. But most people will simply remember that a midpoint is the point in the, middle. Here's a line segment. The point in the middle is here. That is a midpoint since it divides the line segment into two congruent segments. That's all there is to a midpoint. Last item for this section is a segment bisector, and it's once again time for some Latin roots. For the word bisect, we have the first part, bi, which means two. Think bicycle, which has two wheels. Next, we have sect, which means to cut. Therefore, a bisector is something which cuts something else in two. But we are talking about a segment bisector here, so a segment bisector is something that specifically cuts a line segment in two. However, in geometry, bisecting is more specific than just cutting something in two. In geometry, a bisector cuts something into two equal parts, not just any two parts. So we have our line segment back with the midpoint drawn in. Since a segment bisector cuts a line segment in half, a segment bisector for this line segment must pass through the midpoint. Here, this red line is our segment bisector. It cuts the line segment in half. It goes through the midpoint. Obviously, a segment bisector can be a line, but that's not the only thing that can be a segment bisector. A segment bisector can also be a line segment. As long as it goes through the midpoint, it works. A ray could also be a segment bisector. In fact, anything, whether it is a plane, a triangle, or whatever, as long as it cuts the line segment in half, it counts as a segment bisector.